I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll see the introduction to probabilistic generative model. The probabilistic generative model is a statistical framework that learns to represent data distributions by modeling the underlying probability distributions. These models can generate new data samples that resembles the original data, capturing complex patterns and relationship. Examples include variational autoencoders VAEs and generative adversarial networks GANs, which have applications in image and video generation, data augmentation, and more. By learning probabilistic representations, these models enable uncertainty estimation, sampling, and generation of diverse data instances. Next, we'll see the introduction to the probabilistic models. So, in this case, the generative models are statistical tools that aim to model the underlying distributions, as I've said, of data set so that new similar data can be generated. From this, new data can be generated. Rather than just distinguishing between classes, they try to understand how data is formed, enabling the creation of synthetic data points that resembles the training data. And it is used in the supervised learning. How in supervised learning, generative models are employed to learn the structure of data without needing labeled outputs. Whereas in the supervised, we have to label the data. They analyze patterns in the input to estimate the underlying probability distributions, making them useful for tasks where explicit outputs are not known. And next, estimating the likelihood involves calculating how probable a particular data point is under a given model. This helps in identifying anomalies or generating data points that align well with the overall data structure. Next, learning the joint probability, that is P of xy. It means capturing the relationship between input variable x and the corresponding labeled or output y. This is a function in probabilistic modeling as it forms the basis for the predicting outputs from the inputs. And the popular examples of generative models include naive Bayes, which assumes further independence, hidden Markov models, this we are calling it as HMMS, which models sequences, and generative adversarial, adversarial networks, GANs, which generate highly realistic synthetic data through adversarial training. Next, role of Bayes theorem in generative models. The Bayes theorem plays a vital role in this generative model. Generative model calculate P of y given x, the probability of label the given the input by first estimating the joint probability, that is P of xy, joint probability P of xy, the or that is, and applying the Bayes theorem. This approach contrasts with the discriminative models that directly estimate P of y given x. Bayes theorem, what to say, y given x and equal to P of x given y into P of y divided by P of x, and without modeling the joint distribution. Bayes theorem provides a mathematical rules for updating our beliefs about the hypothesis y given new evidence x. It does this by expressing P of y given x. We are writing like this as the ratio of the likelihood P of xy into P of y divided by P of x. So in generative models, the focus here, the generative model focus lies in understanding the data generation process by making probabilistic assumptions about how the observed data could arise from different classes or distributions rather than merely drawing decision boundaries. Next slide, that is, we'll see the naive Bayes classifier, the overview of the naive Bayes classifier. The naive Bayes classifier is a functional machine learning model that uses the Bayes theorem to predict class membership probabilities. It is widely used due to its conceptual simplicity and efficient training process. Next, it makes a simplifying assumption that all features in the dataset are conditionally independent given the class label. This naive assumption rarely holds in real data, but the model still performs well in practice. One of the strengths of the naive base is its scalability. How means the number of parameter it needs to estimate grows linearly with the number of features, making it ideal for applications involving high dimensional data like text classification. Next, naive-Bayes step-by-step procedure. The first step is naive-Bayes algorithm is calculate the prior probability P of y for each class, which reflects how common each class is in the training data set. Next, then for every feature AXI, the model computes the conditional probability P of xi given y, how likely the feature is to occur with each class. This step assumes independence between features. For new data points, the model calculates the likelihood of the entire feature set given the class using the product rule, that is product of P of x given xi given y, and that is leveraging the independent assumptions. After calculating the likelihood for all classes, the model uses the base Bayes theorem to compute the posterior probability for each class and selects the class with the highest posterior as the predicted label. Next, why naive Bayes works well. This is very important point. Despite the unrealistic assumption of feature independence, naive Bayes often performs surprisingly well because it often effectively captures patterns that dominates the classification task, especially in domains where feature correlation does not drastically affect decisions. And naive Bayes is computationally efficient because its training phase consists of simple count and probability calculations, making it suitable for large data sets and real-time applications. And the model simplicity, it combined with its decent performances, make it good first choice in applications where speed is critical, such as email spam filtering or text categorization. Next, the conditional probability definition, which is used in the probabilistic generative model. And the conditional probability measures the chance of event B occurring even the event A has already happened. It adjusts the probability space to focus only on the scenarios where A is true and measures the proportion of those in which B also occurs. Probability of A intersection B divided by probability of A. Once event A has occurred, it becomes the new reference or sample space. This reshaping of the context allows the model to re-evaluate the likelihood of other events under this new condition. If A and B are mutually exclusive, what is the meaning for this? Meaning that they cannot both occur simultaneously. Mutually means they cannot occur simultaneously. Then the conditional probability of A given B is 0, since the intersection of A and B is an empty set. Next, this is the conditional probability. Next, joint probability. The joint probability quantifies how likely it is for two or more events to occur at the same time. For instance, it can tell us the probability that will rain and that a person will carry an umbrella. When an event A and B are independent, the occurrence of one does not affect the other. So the joint probability simplifies to its the product of their individual probabilities. If A and B are dependent, their joint probability is calculated using the conditional probability. See here, probability of A intersection B here, independent event A intersection B is equal to probability of A into probability of B. Dependent events are A intersection B, probability of A dot probability of B given A, which accounts for the influence of one of the event to the others. Next, visualizing conditional and joint probabilities. And we have to use Venn diagram. The Venn diagrams helps illustrate how events overlap in probability space. They are useful for visualizing intersections, joint probability, and difference between events, making abstract relationship more tangible. The diagrams are helpful for representing sequences of event and conditional dependencies. Each branch in the tree represents a probability pathway, allowing step-by-step conclusion calculations of compound probabilities. Those visual tools help clarify complex probability problems and provide intuitive insights into how different events and their probabilities relate to each other. So, Venn diagram and the tree diagrams are mainly used. Next, Bayes theorem. We have seen it already. The Bayes theorem provides the formal mechanism to revise existing beliefs, that is, prior probabilities, in light of new evidence, that is, likelihood. It is a foundational principle in the probabilistic reasoning and statistical inference. The theorem is mathematically written as A given B is equal to probability of B given A into probability of A divided by probability of B. This Bayes theorem enables us to turn likelihood, which is often more accessible, into the posterior probability, which is what we ultimately want in many real world problems. Next, how the real Bayes theorem is used in the real world problems, real usage. In practice, the Bayes theorem is used in various domains like medical diagnostics, where it helps determine the likelihood of disease given test result, and spam filters, where it evaluates whether an email is spam based on its content. And the prior represents the initial belief of knowledge of event before new evidence is introduced. It is often derived from the historical data or expert opinion. The posterior is the updated belief after incorporating the new evidence. This makes Bayes theorem especially powerful for learning in dynamic environments where new data continuously arrives. Next, the Bayes theorem with the partitioning. So, if you are in this situation with multiple hypotheses, we are using it B1, B2, Bn up to, and an event is A. And the partitioning allows us to compute the posterior probability of each hypothesis given an event. This is particularly useful in classification problem with multiple classes. So this is the formula. Probability of bk given a is equal to a given bk into probability of bk is equal to divided by summation of bi into probability of bi. It ensures that all hypotheses are considered and the probabilities are normalized to reflect the unupdated beliefs. The extension of Bayes theorem is essential when dealing with complex problems involving several possible causes for observed data, helping to determine which causes is most probable. So, coming into the summary, the key idea behind a probabilistic generative model is to learn the mechanism that generate the data rather than just classifying it. This makes them versatile for both classification and data generation. The model estimates the joint probability P of xy, allowing them to generate new instances and also infer class labels through conditional probability. And by relying Bayes theorem, generative models like naive Bayes enables inference by converting likelihoods and priors into posteriors, offering a clear probabilistic interpretation of predictions. And the example, naive Bayes exemplifies a generative model that is easy to implement and interpret, yet surprisingly effective in many real world applications, making it a popular teaching and practical tool in AI and machine learning. Hope all you have enjoyed the introduction about the probabilistic generative model. The remaining things we'll discuss in the next lecture. Thank you.